Laplacian on locally symmetric spaces. So Professor Anker, now
so
the
thank
stage
you.
yours.
Okay, thank you. Do you hear me?
Yes, yes, we can hear you.
Okay, fine.
And your
thank you for the invitation and it's I have a very good memory from nice memory from my stay last December in Ghent, and it's a pity that we can all of us we cannot enjoy the nice atmosphere in your group during this conference. So the topic I will talk about is actually an observation I have made while working with my PhD student Hong-Wei Zhang on dispersive PDEs on symmetric spaces. And at some point, we needed to use the so-called Poincaré series, and we noticed that actually the results available in the literature was not as optimal in higher rank as one may hope. And so we wrote this article I'm going to talk about today. So the setting of my talk is the following. I am considering a Riemannian symmetric space of the non-compact type. So this means that it's a quotient G by K, where G is a semi-simple Lie group with the usual assumptions, and K is a maximal compact subgroup of G. And so the most famous example is the hyperbolic plane, or more generally the class of hyperbolic spaces. So these are Riemannian manifolds with essentially non-positive curvature. And now I want to consider quotients of these Riemannian symmetric spaces. So I take a discrete subgroup of G, which is torsion-free. So it means it has no element of finite order. And if gamma acts on X, it has no fixed point. And the quotient by gamma, which I called Y, is a so-called locally symmetric space. And it inherits the Riemannian structure of the symmetric space X. So you see on the screen a picture of a locally symmetric space of dimension 2. So it can be compact, or it can have cusps like here on the right, or it can have also larger ends. So I need a little some structure of symmetric spaces. So for a semi-simple Lie group G, there is a so-called Cartan decomposition, which corresponds in the symmetric space to polar decomposition. So for instance, for hyperbolic spaces, this A is just a half line, this A plus is just a half line, and the decomposition here on the right hand side is polar decomposition with respect to geodesics. And in so-called higher rank, A plus is a positive cone. I mean, such cones appeared already in the previous talk. And the dimension of A is called the rank of the symmetric space or of the locally symmetric space. And just one more ingredient, if I write down the Haar measure in this Cartan decomposition, then there is two integrals over k, and with respect to the central variable in the cone, then there is a weight here, omega, which has essentially an exponential growth, and this exponential growth is governed by a vector which lies roughly in the middle of this cone, of this Weil chamber. Okay, so this is the basic structure of symmetric spaces and locally symmetric spaces. Now, on this spaces, of course, since there is a Riemannian structure, I have a Laplacian on X, on the symmetric space, and also a Laplacian on the quotient of X by the discrete subgroup. And I'm looking at the bottom of the L2 spectrum of, so for me the Laplacian is negative. So if I take minus the Laplacian, it becomes a positive operator. And on the symmetric space, the bottom of the L2 spectrum, it's known, it's a positive number, which is exactly the norm to the square of this vector rho. And on the quotient on Y, the bottom of the spectrum of the Laplacian is a number which I call lambda 0, and which is between 0 and rho square. So in the title of my talk, I was the bottom is this lambda 0, and one wants to relate this lambda 0 to some other quantities defined on the locally symmetric space, namely the critical exponent of the Poincaré series. So let me explain what is the Poincaré series. So the Poincaré series is the sum of so negative exponentials. So I fix S, a positive number, and I take the sum over the discrete group of e to the minus s times the distance between yk and gamma of xk, and the sum runs over the discrete subgroup gamma. And of course, it's a sum of positive expressions. It can be infinite or finite, and by using simple considerations based on the triangle inequality, one can easily show that this sum is finite for one couple of points x, y, if only if it converges for all x and y. And the critical exponent delta is the number, the critical number s, which is which is the limit point between the regime where this Poincaré series converges and where the Poincaré series diverges. So it's can be, for instance, it's the infimum of all positive s for which the Poincaré series I have taken, for instance, at the origin, here converges. And this critical exponent can be also is also related to the behavior of the counting function. So the counting function is defined as follows. One take 2 points, xk, yk, in the symmetric space. And then all the images of xk, for instance, under the discrete subgroup gamma, and one counts all the elements in gamma for which this distance is smaller than capital R. And so this is called the number of points is called the counting function. And in this case, it has an exponential behavior. So if I take the logarithm of this counting function and divide by R, the lim sup can be shown to be equal to this critical exponent delta. So this is a second definition, if you wish, of the critical exponent. And this critical exponent can be shown to be always between 0 and at most 2 rho, so 2 times the norm of rho. Okay, so my goal now is to explain what is the relation between this critical exponent delta and the bottom of the L2 spectrum, which is lambda 0. So this connection is known in for locally symmetric spaces of rank 1. So in rank 1, one has a full list of symmetric spaces. So these are all hyperbolic spaces. The hyperbolic spaces over the real numbers, over the complex numbers, over the quaternions, and also there is an exceptional case over the octonions. And in this table, I have just listed the group G, the group K, corresponding group G, the corresponding subgroup K. What is the dimension of the space, and what is in this case my cone A plus, the Weyl chamber is simply a half line. So rho is just a number, and you see it's roughly half of the dimension. Not exactly, but close to half of the dimension. And now I come to the main result. So this is a result which was proved successively by several authors, Elstrodt, Patterson, Sullivan and Corlette in rank 1. So Corlette did the full case, and this famous result expresses the bottom of the L2 spectrum of the Laplacian, so lambda 0, in terms of delta of this critical exponent. And so you see, you remember delta is always between 0 and 2 rho. So as long as delta is between 0 and rho, so the bottom of the L2 spectrum is the same as on the symmetric space. So it's rho square. And after rho, this lambda 0 starts decreasing. So if you are at exactly a rho, you have here a rho square. but if you go to 2 rho to the maximal value, then this becomes equal to 0. Okay, so I wanted to give at least one proof in my talk. So I will explain the idea of the proof of this theorem. And the link between these two quantities is provided by the green function. So the green function is the kernel of the resolvent. So I take the resolvent of the Laplacian and I write it as, so minus the Laplacian. So it's the inverse of minus the Laplacian minus rho square. This is just here, this minus rho square is a shift to bring the bottom of the L2 spectrum to the origin. And I add this sigma, so this sigma just gives me the spectral gap. And in rank 1, this green function has an explicit expression, can be expressed in terms of the hypergeometric function. So it's a classical special function, and it's rather easy to see that one gets away from 0, one gets an exponential decay, and this exponential decay is exactly given by e to the minus rho plus sigma times r. Okay, so in order to get now the green function on the locally symmetric space, one one simply makes sum over the subgroup gamma, and this gives so one takes the green function, or actually the green kernel is a convolution kernel, and one takes here simply the sum over all gamma in the discrete subgroup, and one gets this way the green function on the quotient on the locally symmetric space. And now there is a criterion which gives exactly the bottom of the L2 spectrum, and this bottom lambda 0 of the L2 spectrum, so is the supremum of all numbers rho square minus sigma square, where sigma is between 0 and rho, and the sum here, this positive sum, converges. So this is really the way to compute this bottom of the L2 spectrum. And now, since the green function has an exponential decay, you see that in this sum here, if one replaces the green function on x by the exponential, then one gets actually the Poincaré series. And so for as long as, so if delta, if the critical exponent is between 0 and rho, then you see that the sum here will always converge for all sigma. And if the critical exponent is between rho and 2 rho, then this sum is converges when sigma is larger than delta minus rho, and is infinite when sigma is smaller than delta minus rho. This is because of the definition of the critical exponents. And so this gives the proof of of theorem 1. I will show it. The fact that lambda 0 is given by this expression. So my purpose now is to talk about the Higherrank case. So the Higherrank case was considered by Leuzinger and his student Weber. This was about 15 years ago. And they obtained a result which was not as precise as theorem 1. So you see lambda 0 is equal to rho square when the critical exponent is small, and until it reaches a number which is smaller than the norm of rho. And then instead of having an equality, one has just a double inequality. So lambda 0 is between two expressions, and one has various expressions depending on the range of delta. And in order to prove this theorem, Leuzinger used an estimate of the green function, which I obtained with Leuzinger in the end of the 90s. And so this green function has a behavior. This symbol here means that the left-hand side and the right-hand side have a quotient which is between two positive, which means between two positive constants. And so, of course, the behavior near the origin is well known. It's like in the Euclidean case, but the behavior for large variable is given by this expression here. So you see there is an exponential factor which actually mixes a decay which depends on the norm of R, and also some inner product of R with rho. And there is some polynomial factor here in front which doesn't play an important role. And R is the component of y minus 1x in the Cartan decomposition. So in the Weil chamber. Okay, so this is the result, and actually this the observation is that this result can be made much more precise. And in order to make it more precise, I consider different Poincaré series. So the first Poincaré series here is, instead of defining it in terms of the Riemannian distance, I define it in terms of some kind of polyhedric distance. So it's given by the inner product of here y minus 1x, the component in the Cartan decomposition, and the inner product with this vector rho divided by its norm. And so this distance is actually, if you consider balls, then these are polyhedric balls, and which have already proved to be much more related with growth and structure of symmetric spaces than the spherical balls. And now one defines in the same way critical exponent for this modified, for this new distance. And it can be also related to some counting function. And one obtains then the following theorem. And you see that there is a small improvement with respect to theorem 2, in the sense that now delta prime can go between 0 and half of the full range. So the result is exactly the same as in rank 1. And above rho, there is still a double inequality. So this may look unsatisfactory, and we are going to improve it. So in order to improve this result, I will consider a second Poincaré series. And for this second Poincaré series, I consider now a distance which is a mixture of the Riemannian distance d and of this polyhedric distance d prime. So this d depends on a parameter s. So if s is small, then this is simply s times the polyhedric distance. But if s is larger than rho, then it's a mixture of the Riemannian distance and of this polyhedric distance. So with this family here of distances, I can construct Poincaré series. And of course, there is an associated modified critical exponent. And this modified critical exponent, delta seconds, is larger than the first critical exponent delta, which is associated to the classical Poincaré series. And it's smaller than the delta prime, which was defined in the first improvement. And now with the help of this delta second, we can get the exact analog of the theorem 1 in rank 1. So you see to have an explicit expression of the bottom of the L2 spectrum. It's equal to rho square when this new critical exponent is between 0 and half of the range. And it's equal to rho square minus, so delta second minus rho square, if you are in the second half of the full range. So theorem 4 is really the highest rank analog of theorem 1 in rank 1. And the reason why one consider these distances, which may look a little bit strange, actually it comes from really the behavior of the green function. I will show it again. So you see the green function, really the exponential decay of the green function is a mixture of an expression here which is related to the Riemannian distance and another expression here which is related to this polyhedric distance. Okay, and in order to conclude, I will just give an application. So in the lattice case, so a lattice is a discrete subgroup such that the quotient has finite volume. So there are many examples and interesting examples of such discrete subgroups. And so if gamma is a lattice, then of course the function 1 is an eigenfunction of the Laplacian corresponding to the eigenvalue 0. And all critical exponents are equal to 2 rho. Now, what is interesting is the fact that there is converse statements. And the converse statement is the following. If G has the property T of Kazhdan, then actually the following conditions are equivalent. Namely, gamma is a lattice if and only if the bottom of the L2 spectrum is 0, or if and only if delta is equal to 2 rho, or the same statement with the delta second. Actually, this result was already observed by Leuzinger, except for the last characterization, but the first 3 characterizations were already observed by him. And in order to finish with the question, we have not been able to see if we guess that we conjecture that the condition delta prime is equal to 2 rho is also equivalent, but we have not been able to prove it so far. So thank you for your attention.
Thank you very much, Jean-Philippe, for this interesting talk. So we are open for question now. So are there any questions?
Can I ask a question?
Yes, sir.
Is it possible to also give a characterization in terms of the decay of the heat kernel?
Excuse me?
Sorry, is it also possible to give a characterization in terms of the decay of the heat kernel?
Yes, I mean I prepared first some additional slides about the heat kernel. Weber actually computed obtained an upper bound of the heat kernel, which was in terms of the critical exponents. And it's not, I mean, the result is a little bit technical to state. And with Hong-Wei Zhang, actually, we obtained a slightly better statement. The proof is exactly the same, but the statement, the bound is a little bit better, looks a little bit better. Did I understand? Did I answer your question?
Yes, yes, I think because it's this bottom of the spectrum also relates very, you know, to the decay of the heat kernel and also this critical exponent. So I was thinking that maybe it's also, you brought in the functional calculus via the green kernel. So I thought that maybe there are some equivalence formulations or characterization in that context. So thank you for, thank you.
Yes. If you look at, I put on the first page, and also in the abstract, the reference to the preprint in arXiv. So if you look there, you will see exactly what is the bound, the precise bound that one can obtain.
Okay, thank you.
Okay, thank you. Some more question? Any other question?
Yeah, maybe I can ask a naive question, because that's really not my field of expertise. But so the splitting of the range between, say, absolute value of rho and twice that value, I guess there is some deeper meaning for that. Or could you enlighten us a little bit?
I mean, the critical exponent, it measures in some sense the size of the discrete subgroup. So when delta is small, it means that the discrete subgroup is small, and but the fact that there is this threshold of when delta equal rho is indeed it's well known. I mean, the locally symmetric spaces when delta is smaller than rho are much easier to deal with than the locally symmetric spaces when delta is between rho and 2 rho. But I'm not, as I said, I'm not really a specialist of locally symmetric spaces. I mean, I just noticed that we just noticed when we were working on dispersive equations that actually the proof of Leuzinger was fine, but he just missed the right statements.
Okay, thank you very much.
Okay, thanks David for asking question. And some more question we have? Another one?
I wonder if you can say anything about the wave equation.
Okay. Yes, sure. Go ahead, please. Please.
I wonder if you can say anything about the wave equation from this.
I mean, this is what exactly the subject of the PhD of Hong-Wei Zhang, and he has a paper. You can also find it on arXiv, which has just appeared in the Journal of Geometric Analysis, where he has looked at the wave equation on locally symmetric spaces. But of course, in the most easy case, when the critical exponent is between 0 and rho, not between rho and 2 rho. If you go above, it really becomes very tricky, and I think there are only people like Bourgain, Dyatlov who may know the answer.
Thank you, Jean-Philippe.
Thank you, Tony. So no more question now. Okay, so let us thank the speaker again.
Thank you.
Thank you for having you here. So